In the last video, we wrote the Nernst equation in this form, and there's nothing wrong with this form, so it's totally fine. So E equals E standard minus RT over NF natural log Q. But it's commonly written under conditions of 298 Kelvin like so. So E is E standard minus 0.0592 volts over N times the log of Q, and it's exactly the same. And all we've really done here is we've put in the value of F, we've put in the value of R, we've put in room temperature 298 Kelvin, and we've converted natural log to base 10 log. It's just a factor of 2.303 difference in there. And this is a common form of the equation. So this is a very common way to actually use and manipulate the Nernst equation. So for instance, let's build a cell, and the cell we're going to build is going to look something like this. We're going to have a zinc electrode in contact with zinc. Let's say it's going to be standard conditions 1 mole per liter. And on the right hand side, we're going to have a standard hydrogen electrode. So we're going to have hydrogen gas in contact with hydrogen ions. And maybe we're going to make that, I don't know, X moles per liter. And we're going to need the electrode to hook it all up. So we're going to use platinum on the right hand side. So E cell, okay, is E right hand side minus E left hand side. So we know that the standard hydrogen electrode would be 0, so it's just that minus the zinc electrode. Okay, so that is 0 minus 0.76 volts, so that is positive 0.76 volts. And if we apply our Nernst equation to that, we'll go ahead and need to know what the reaction quotient is. We'll need to know the number of moles of electrons transferred. So I suppose we should write out the chemical equation. So we've got zinc going to zinc ions plus 2 electrons. The easiest way to remember is that it essentially goes left to right, or if you like, this is the anode, so this is oxidation, so you're going to lose electrons. Electrons are negative, oops. And on the other side, you've got reduction, so you've got the gaining of electrons, so that must be hydrogen is gaining electrons, so I got 2 H pluses plus 2 electrons goes to H2. Okay, and if I sum those together, I can see that they sum together because those 2 electrons would cancel out, so I've got my zinc solid plus my 2 hydrogen ions on the left, and on the right I've got my zinc ions plus my hydrogen gas. All right, so what do we got here? So the reaction quotient Q is the products over reactants. So I've got hydrogen gas on the right, so it's going to be the pressure of hydrogen. I've got zinc ions on the right, so it's going to be the concentration of zinc. So this is the thermodynamic reaction quotient, where we use pressures for gases and concentrations for solutes. On the left, I've got zinc, so it's a solid, so it doesn't enter. And I also have hydrogen ions, so since they are a solute, I'm going to do that. And what else do I have here? Oh, that's kind of naughty, right? So the hydrogen, I'm going to have it as 1 atmosphere. And so that means that that will be a 1. And that will be a 1. So essentially the reaction quotient then is just 1 over the concentration of H plus squared. So I can go ahead now and I can write my Nernst equation using this new form. So I can say the cell voltage is their standard cell voltage, so plus 0.76 volts minus 0.0592 volts over N. So that was a 2 electron transfer. So I'm going to write 2 right there, times by the logarithm of Q, so that was 1 over the concentration of H plus squared. So we could see actually that by varying the concentration of H plus, we will see a variable voltage. So we've basically built ourselves a pH meter. And if we want to go ahead and play a little bit further, we can play a little bit harder with this equation, and let me move everything up and show you. So first of all, we have to know a few things about log. So if we take the log of 1 over x, okay, that's the same as log of x to the minus 1, which is minus log x. And we also know that the log of x to the n is equal to n times by the log of x. So we can actually manipulate this last term here in the expression by applying those 2 rules. So the cell voltage that we get is equal to 0.76 volts. All right, let's see here. So we've got 1 over something. So 1 over something is like raising it to the minus 1 power. So we can bring that minus 1 power out front. That'll convert that to a plus. And the second thing is that we'll have a squared there. And so we can bring that power out front. And of course, the 2 and the 2 cancel out. So this gives us a very nice equation. times by the log of the H plus ion. In fact, we might say, gosh, that's reminding us of pH. pH is just minus the log of the H plus ion. So if we measure the cell voltage, we can show it's related to the pH by just saying it's equal to minus 0.0592 volts times by minus log H plus, so that is pH. So essentially, we have created ourselves a pH meter. And in the pH meter, every time the pH changes by 1 unit, the voltage changes by 0.0592 volts, or 59.2 millivolts. So when we calibrate a pH meter in the lab, we are making sure that every time the pH changes by 1 unit, the voltage is changing by 59.2 millivolts. So that, my friends, is how we would use the Nernst equation to make ourselves a pH meter. Nice, huh?